hours tomorrow. I don't know if any of you were planning to come tomorrow at 2. So as I already got an email, instead I will do the online office hours via phones. So that will be 6 to 7 p.m. tomorrow. So I will sit at my computer. It's there waiting for questions. So if anyone wants to participate, make appointments, so that's not a problem. The other thing is, I just remind you of the survey. I think I looked today and 5 people had participated. Okay. All right. We're talking about photosynthesis and this reaction that starts when light is absorbed somewhere within the photosystem. Excitons get transferred to the reaction center. And I want to just discuss events that are in the reaction center and just finish some aspects of this. We're still on electron transport, and I showed this cartoon for green plants where there's 2 photosystems, photosystem 1 that I spent most of the time on, but there's also this photosystem 2. So this is one way to illustrate this, what goes on in plants and photosynthesis. But the other way to illustrate it is the so-called Z scheme. So I would just like to point out some things that are shown by the Z scheme. So for the Z scheme, we have P700, which represents the special pair of chlorophylls in photosystem 1. And we have P700 star. And ferredoxin is about here. And then AMP is here. Roughly, this is not a very accurate diagram. And then P680, so this is photosystem 1. P680 is over here, and P680 star, and there's some other things in between. All right, so the Z scheme illustrates 3 things, and it does so in a somewhat quantitative way. One is it illustrates the sequence, it illustrates absorption of light, right? So these upward arrows represent excitation of P700 or P680 upon absorbing a photon of light. In addition, it illustrates the path of electrons. So electrons go from the excited P700 star to ferredoxin, and then from the protein ferredoxin, they go to NADP to make NADPH. Right? So labels in order. So that arrow, that blue arrow represents excitation, but those blue arrows represent electron transport. And so this is focusing on photosystem 1. Now the other thing that I find interesting about this diagram is that the y-axis is a quantitative measure of reduction potential. And note that the positive numbers are near the bottom. So for photosystem 1, P700 is about plus 0.4. P680 turns out to be about plus 1.0. Right, so positive numbers are towards the bottom, and negative numbers are near the top. And so what is P700 is greater than 2. So maybe let's say this is minus 1. And let's remember what reduction potentials tell us qualitatively.
If it's positive, then it means that it's really spontaneous.
Positive means a strong oxidizing agent.
Oh wait, no, that's so.
And negative means weak oxidizing agent, therefore strong reducing agent. So I want to focus, as the slide is, I want to focus, at least to start, on photosystem 1. And so maybe I'll erase for now the photosystem 2 part. And first of all, look at some of the numbers. So P700 the reduction potential of P700 is about plus 0.4 volts. The question is, what reaction does that actually refer to? Well, reduction potentials always refer to reduction reactions. So what's the reduction reaction that refers to? The reduction reaction that refers to is this one. P700 plus an electron to make P700. So that's what it means to say P700 has that reduction potential. It means that the oxidized P700 accepting an electron. Right? What about P700 star? What's the reduction potential of P700 star, and what reaction does that refer to? The reduction potential of P700 star is about minus 1.2. That's a big number. It's a negative number, which means this is a strong reducing agent. But again, what's it referring to? What is the reducing agent? Well, in this case, the reduction potential refers to this reaction. Again, it's the oxidized form of P700, because it has to accept an electron. It's going to accept one electron, but the reduction potential refers to this reaction where oxidized P700 accepts an electron in the excited state. That's what this reduction potential of minus 1.2 volts refers to. Let's say that's the reaction. But the other thing is, again, what does it refer to, or what does it tell us? It tells us that this thing, the excited P700 star, is a very strong reducing agent. And it's a much stronger reducing agent with the ground state of P700. Right? And that's what we said we needed. We need a strong reducing agent to be able to get electrons into NADP. So let's look at what these numbers tell us. Let's consider two possible reduction reactions. Both are going to involve NADP, accepting electrons. Let's first consider a hypothetical reaction where two P700s in the ground state donate electrons to NADP. To make two NADPHs. All right, the reduction potential of P700 star, P700 is plus 0.4. NADP is about minus 0.32. The delta E for this reaction is minus 0.32 minus 0.4, which is minus 0.72 volts. A negative delta E tells us the reaction is not spontaneous. If you want to, you can figure out the delta G for this reaction. Delta G 0 prime is plus 139 kilojoules per mole. So this is not the reaction that happens in vivo, obviously, because this is not a very strong reducing agent. It's not strong enough to get electrons into NADP. Instead, you need this P700 star with a very large and negative reduction potential. Now this is a strong enough reducing agent to get electrons into NADP. Of course, this is the actual reaction that happens in photosynthesis. Note that the products are the same. The products are both oxidized P700 plus and NADPH, but now we have a different reducing agent. And so you can calculate at home calculate delta E for yourself at home, and then from that you can calculate what delta G is. And obviously delta E is going to be positive, and obviously delta G is going to be a large negative number. So it's actually very large. So this Z scheme illustrates kind of what I said already before, but the excitation of this thing takes, again, a very weak reducing agent and makes it a much stronger. And so you get this excited P700 star. It's a strong enough reducing agent to reduce NADP, so this reaction is spontaneous, as I just said here, and as you can calculate upon. All right, so that's sort of the right-hand side of the Z scheme. The other side of it is, again, as I indicated last time, the rest of the Z scheme exists to get electrons back into P700 plus to reduce it back to where it started. So let's look at the left-hand side of the Z scheme. This is just to remind you of reduction potentials and to show, I just wanted to mention that ferredoxin is a very strong reducing agent, very large negative reduction potential. So the reaction of ferredoxin reducing ADP is spontaneous as well. You can do the calculation for those molecules as well. All right. Let me go on to photosystem 2. All right, so this is to remind us of what happens in photosystem 1, right? So light is absorbed, chlorophyll gets excited, electrons are transferred to ferredoxin, they get carried, those electrons are carried away. What I said last time is that this protein plasmocyanin then gives electrons back to the chlorophyll. So plasmocyanin is going to donate an electron to the oxidized form of photosystem 1, or to P700 plus. So let's look at that reaction. I hope my next slide is going to show that. All right, so here's the cartoon version. Here's photosystem 2. Here's plasmocyanin over here. But again, electrons are going to flow from the photosystem to plasmocyanin. Note that water is now finally going to be the source of electrons. So photosystem 2 is going to enable electrons to essentially go from water to plasmocyanin. All right, so here's the Z scheme. So we do redox reactions reduce P700 plus. So P700 plus is going to be the oxidizing agent, and the reducing agent is going to be P680 star. Excited form, yes.
Can you clarify the stoichiometry for the top reaction? The two
the top reaction.
The two NADPHs.
Oh, sorry, it shouldn't be 2, it should be 1. I got mixed up there.
Gotcha.
It has to be 2 P700s, but it's
That's what I thought. All right, thanks.
This reaction we can just do as one of each. So P700 is going to be reduced, and the P680 is going to end up in the oxidized form. P680 plus. The reduction potential of P700 plus is about plus 0.4. So it's a moderately strong oxidizing agent, I think. Well, let's look at that. But what you see is that P680 star is, again, a pretty strong reducing agent. Its reduction potential is about -1. And so again, if you figure out the delta E and delta G, you'll find that, figure out these. But again, electrons are going from a strong reducing agent to a moderately strong oxidizing. The figure, all right, so the Z scheme shows us that. It shows us P680, P680 star being a relatively strong reducing agent. And so electrons going from strong reducing agent to relatively strong oxidizing agent. It also shows the path of the electrons. And I just want to point out a little bit about the path. And again, as always, I'm not concerned with all of the details, but what are the electron carriers? Among the electron carriers are this molecule called plastoquinone, which in this slide is abbreviated as PQ. So plastoquinone is a type of quinone, and its structure is that it has a 6-membered ring, which can be in the oxidized quinone form, and I believe these are methyl groups. I'll show the structure to make sure. And then there's a hydrocarbon chain, but this is the oxidized form of plastoquinone. And so it's very similar structurally to coenzyme Q. This molecule can accept 1 electron and 1 proton to form a semiquinone structure that I won't draw. And the semiquinone can accept a 2nd electron and a 2nd proton to make the hydroquinone, the fully reduced form. So this would be PQ. So chemically, it's virtually identical to coenzyme Q.
Wait, why are they both PH2? Wouldn't that be the oxidized form?
Just trying to make sure you guys are awake. It's working. Here's the oxidized form, and so this is the structure. Note again this long hydrocarbon chain, 9 of these isoprene units, and then I won't even try this by memory. This is coenzyme Q. And so they're the same. They have the same quinone ring. Note that this has methoxy groups. This has methyls. They both have this long hydrocarbon chain. Right? So it's essentially the same chemical structure and same chemistry. All right, so in the Z steam, electrons are going to be passed from the excited P680 to these quinones. Quinones can then diffuse away, just like coenzyme Q in mitochondria, and they diffuse to this protein complex called cytochrome B6F complex. And I just want to say a few words about cytochrome B6F. Cytochrome B6F is a multi-protein complex which is found in the thylakoid membrane. And it catalyzes a reaction which is in some ways analogous to complex 3 of mitochondrial electron transport. Right, so the reaction that it catalyzes is in that reaction is that it takes a reduced plastoquinone, 2 molecules of plastocyanin, and oxidized, and it reduces the oxidizes the plastoquinone, reduces the plastocyanin, and produces 2 protons. So those 2 protons are these 2 protons. And this is all happening in the thylakoid membrane. So where do those protons go? These protons are released into the lumen of those thylakoid compartments. But these protons originated from the stroma. When the coenzyme Q was reduced during these electron transfers, protons were taken from the stroma to make the reduced PQ. But when it's reoxidized, they're released to the other side. Right? So this is proton pumping. And so in this respect, this enzyme functions similarly to complex 3. The mechanism is, again, thought to be the Q cycle, which I didn't describe in any detail for complex 3, and I'm not going to describe it here either. But remember that complex 3, although complex 3 only uses one coenzyme Q as a substrate in the net reaction, complex 3 pumped 4 protons rather than 2. And so actually, this guy does the same thing. It pumps 4 protons per PQ that gets oxidized. So again, the mechanism is that protons that are taken from the stroma side get released on the lumen side, and the mechanism is the Q cycle. And so I should have described the Q cycle again. I'll describe it in office hours. All right, so here's the reaction. This is cytochrome B6F, so several protein subunits. The net reaction is that it oxidizes the reduced plasticinone, and electrons are given up to plasticyanine, which carries it away. And again, what they're showing is that 4 protons are being pumped across. So this is unlike in mitochondria, where there's 3 complexes that will pump protons. This is actually the only protein complex that pumps protons.
So 2 of the protons come from the PQH2. Where do the other 2 come from?
So it turns out all 4 of them come from PQH2.
Oh.
It has to do with, if you look in this figure, this PQH2 has 2 electrons. So one of them goes to plasticyanine, which can only take 1 electron. So what happens to the other one? The other one actually goes to another PQ and makes a semiquinone. A second PQH2 comes in, gives one of its electrons to this copper, to a different plasticyanine. Its 2 protons get pumped, and its second electron goes to this PQ semiquinone to make a PQH2. So that's the Q cycle. The net reaction is that 1 PQH2 is oxidized. The actual mechanism is that actually 2 of them get oxidized, and all 4 of those protons end up on the other side. So, and that actually applies to complex 3 as well. So it's complicated. It's not as complicated as I was thinking. I think the figure earlier in the chapter shows it for complex 3. Okay. So that's a very important part of this process. And again, this is finally going to get electrons to plasticyanine. The copper is reduced to copper +1, and that's the electron that can then be given to the oxidized. All right, so to recap, P700 was excited. It gave up electrons to FAD, or sorry, to ferredoxin and eventually an ATP. The P700 was reduced back to where it started, using electrons that came from P680 star, carried by plasticquinone, plasticyanine, via cytochrome B6F. So now we're left with oxidized P680. And so to finish the story, we have to reduce P680 back to where it started. So there's oxidized P680, P680 plus. So to finish the reaction, we've got P680 plus. And we need to reduce P680 plus back to P680. So we need a reducing agent. The reducing agent is water. So 1 mole of water will reduce 2 P680 pluses. Make 2 P680. We'll get a half a mole of O2, and I guess we'll get 2 protons. Okay. So now finally water comes into the picture. Water is a lousy reducing agent. The reduction potential of oxygen is plus 0.816 volts. Oxygen, strong oxidizing agent, therefore water, weak reducing agent. So we're trying to use a very weak reducing agent. Fortunately, P680 plus is a very strong oxidizing agent, as you see from the Z scheme. The reduction potential of this is on the order of plus 1 volts. Right, so that's the largest positive reduction potential, I think, of anything we've seen, and that's the strongest oxidizing agent of anything we see. So this is a very strong oxidizing agent. And you can think of it as strong enough to pull electrons out of water, which water really doesn't want to give up those electrons. But it can do it, and so at home you can figure out this and this. But again, clearly delta G is going to be negative for this reaction. So that's the very last part of this. Of course, as far as humans go, this is very important because this is where all the oxygen we breathe comes from. This reaction is catalyzed by the so-called oxygen evolving complex, which I'm not going to discuss. Catalyzes this reaction. I think the next slide shows more details of this. So I'll show this. So this is what's going on in P680. This is P680. There's the 2 special pair of chlorophylls in P680. So electrons went out of P680 to plastoquinones. This, I guess, is one that carries them away to the site of P6F. And now here's electrons that originate in water being transferred to reduce this back to the original pieces. So this sort of completes the overall reaction, and again makes the oxygen. Yes.
Does the breakdown of water occur within the reaction
It's I think it's within the photosystem. It's a separate part of it. It's a separate enzyme called the oxygen evolving complex. This little bit here is 4 nanometers, it turns out. So it's got its own molecules. But it has to get electrons. It's all part of it. Okay. So that's all I have to say about electron transport in this class. Any questions? Before you on ATP synthesis? I really said the important things about ATP synthesis. Okay, so here's the cartoon that indicates ATP synthesis. So in this cartoon, again, here's photosystem 1, NADP being reduced in ATPH. Here's photosystem 2, so getting electrons from water. And here's cytochrome B6F. So, but now what they've added is the ATP synthase. So the ATP synthase is called CFO-CF1, but it's the same, structurally, essentially the same as the ATP synthase in mitochondria. So this is the ATP synthase in chloroplasts. The cartoon that's shown in this slide looks similar to the cartoons that were shown for mitochondria. You have a proton channel in the membrane. You have an A subunit and a C subunit that together allow protons to pass through the membrane. You have alpha and beta subunits that synthesize ATP. You have a gamma subunit that connects the alphas and betas to the ring C subunit. So the mechanism is exactly the same. Structurally, it's the same. Right? It's a different set of proteins than mitochondria. But other than that, it's completely the same. So we don't have to go into any detail on this. I just point out that this slide also summarizes the protons and where they're coming from. So here's the 4 protons that are coming from the cytochrome B6F complex. So these protons, again, are the ones that came from plastoquinone. This slide shows explicitly that when plastoquinone is reduced, the protons come from the stroma, which is the N side in this context. Right? So protons are picked up from that side, but they're released on this side. It also indicates that these protons that came from water are also produced in the lumen. Right? So those 2 protons are new protons in a sense. And so they're contributing to the proton concentration in here. And I think you could also count this proton that when NADPH is reduced, or NADP is reduced, it picks up a proton. So there's going to be 1 less proton out here for every NADPH. Right? So all those things together cause the proton concentration on this side to be much greater than it is on the other side. Right? So that's going to mean that the flow of protons is going to be spontaneous. It's going to have a large negative free energy change. And it turns out, maybe these numbers from the book, but the stroma, the pH can be about 8, but in the lumen, the pH can be much lower, about 5. Right? So that's 1,000 times greater concentration of protons in the lumen than in the stroma. So that's a very large difference in concentration, which provides a very large thermodynamic driving force that can be used to make it.
That would be the same with the mitochondria.
I think it's not quite as big as the mitochondria. I don't think it gets as low as 5. I don't know. Maybe I'm wrong. But it's certainly a big difference. All right, so that's easy. We've already learned about it. I do want to mention one other thing, which is a unique feature of photosynthesis. And I just point this out. I don't want to read it about home, So in photosynthesis, P700 becomes excited to make P700 star, so strong release agent. And then electrons one electron is passed to ferredoxin to make the reduced ferredoxin. And then to make NADPH, that electron has to be given to NADP. But what's shown on this slide is that there's another possible way to use that electron. And the other way to use that electron is to transfer it to plastoquinone, I believe. Yeah, the electron can actually be transferred to an oxidized PQ to make PQH2. And then the electron can be transferred from PQH2 back to P700. So this is what's indicated on the slide as cyclic electron flow. So P700 is excited, electrons get transferred to ferredoxin, and then they get shuttled back to P700. So this is something that, so why would a plant do this? It seems kind of pointless, right? But it's not pointless because what they're showing on the slide is that these electrons are being transferred to P700 via the cytochrome B6F complex. Right? So cytochrome B6F is involved in cyclic electron flow, and so cytochrome B6F pumps protons. Right, so cyclic electron flow is a way for the plant to be able to make ATP because the protons get pumped, so you get a proton concentration gradient. And because the electrons never found their way to NADP, it's a way to make ATP but not make NADPH. And so apparently there are times that I guess the plant has as much NADPH as it needs, but it still wants to make ATP. So this variation on this pathway provides a way to do that. Apparently this is regulated, so the plant can either do regular photosynthesis that I described, or it can do this cyclic pathway when it needs to. So this is kind of interesting. This is something that, of course, could never happen in mitochondria, right? You can't have this sort of, you can't have this kind of cyclic process and still make ATP in mitochondria. Right? So that would be like taking electrons from NADH and putting them into complex 1 and eventually giving them back to NADH but still making ATP. You can't do that in mitochondria, but you can do that in photosynthesis. So you can think about why you can do it in photosynthesis but not in mitochondria. The answer is maybe. I don't know. I think the answer is obvious, but that's because I read it in the book.
I'm not reading that book.
Questions? Yes.
How is this regulated?
So how is it regulated? I don't know the details. I jotted something in my notes that apparently depends on light, how much light there is. And so I'm not sure whether you want to make more ATP or less when it's light. But apparently it depends on. But apparently this PQH2, what I wrote down is that it binds to and it stimulates a kinase, and the kinase must phosphorylate. So but apparently there is there's a set of enzymes that yes.
In what conditions would the plant cell want ATP but not NADP?
This simple answer, and the only answer I can give you is if it's got a lot of NADPH, I suppose it's not making a lot of fatty acids. It wants to make glucose. I think but most under a lot of conditions, this is like the only way to make it. It's not like it's getting it from something.
You don't know.
Any other? All right. So, let me just show this figure. This is a nice figure in chapter 19, which sort of relates electron transport, oxidative phosphorylation, and photosynthesis. So this is just to remind us in mitochondria, we have an N side and a P side. Protons go from the matrix to the intramembrane space and then back to the matrix. In bacteria, I said this, and this figure shows this, that the N side is the cytoplasm of the bacteria, it's cytosol, and protons get pumped outside into, at least in E. coli, the intramembrane space, and they flow back in. And so then, in chloroplasts, this is what I said, is the luminous P side and the strong is the N side. I'm not sure what the reverse is. So that kind of summarizes it. And I think that's the last thing I have to say about the light reactions of photosynthesis. So I don't want to say very much about the dark reactions. I'll say a little bit today and probably have to spend more time Friday. But again, remember that the light reactions, the purpose of the light reactions is to provide NADPH and ATP. And then those are used in these, what they're calling carbon assimilation reactions. But really the NADPH and ATP can be used in all the biosynthesis that the plant needs to do. So the Calvin cycle focuses on taking CO2 and making it into carbohydrate. And that's what I'll discuss. But I think before that, I will show. All right, so just for completeness, all of this is happening in the stroma of the chloroplast. This slide really summarizes in a bigger picture way. This is from chapter 20. So here's ATP and NADPH that are used, or that are made by the light reactions. The carbon assimilation reaction involves taking CO2 from the atmosphere, fixing it into material inside the plant, and as I said last week, I think, the first thing that the CO2 is found in is triose-phosphates, in other words, 3 carbon molecules. 3-phosphoglycerate is a molecule. Now actually, this figure is not quite right because the ATP is not really used here. But the ATP would be used, for example, to take these 3 carbon molecules and make 6 carbon molecules, like glucose 6-phosphate, which is then used to make cellulose or starch or sucrose. But glucose 6-phosphate, we know can be made into ribose 5-phosphate, which could either come from this direction or from this direction. And remember that ribose 5-phosphate is used to make ATP and other nucleotides to make DNA and RNA. They show protein lipid here, but actually the more important way to make lipid is to take the 3-phosphoglycerate that comes from the carbon fixation reaction. So CO2 is fixed in the form of 3-phosphoglycerate. And then to make lipid, to make fatty acids, for example, this is broken down to pyruvate and then to acetyl-CoA. And then that acetyl-CoA can be used to make fatty acids. But again, the carbon atoms in the fatty acids originated as CO2. Amino acids, pyruvate, I've said, can be used to make alanine. So we can make an amino acid from pyruvate. We can make oxaloacetate from the pyruvate. And oxaloacetate can be used to make aspartate and other amino acids. We can make alpha-ketoglutarate from carbons in the pyruvate. Alpha-ketoglutarate is used to make other amino acids as well. So the point is that these carbons that started as CO2 can be used to make basically every molecule the plant needs. So the plant can exist entirely with CO2 as the carbon source, and the oak tree that's 300 feet tall, every carbon atom in the cellulose and the wood all came from CO2. So this is an important process for plants as well as for us. So I don't really have time to give all the details today, so I'll just sort of vamp for a few minutes. This is the Calvin cycle, or sort of a skeletal version of the Calvin cycle, and it involves 3 stages: fixation, reduction, and I've gone through some of this before. The fixation step is the one that I'll say a little bit about, I guess next time. But it involves, this is where the CO2 is actually combined with the ribose 1,5-bisphosphate. The enzyme that catalyzes this reaction is called Rudisco, which is, some would argue, is the most important enzyme on the planet, because all life depends on these carbohydrates. It's also probably the most abundant enzyme on the planet, because there's huge amounts of it in plants. But this is the enzyme that actually takes the CO2 from the atmosphere and uses it to make this molecule 3-phosphoglycerate. So I'll go through the mechanism of that reaction next time. I mentioned, and I won't go into detail, but once we've got 3-phosphoglycerate, we could, for example, use it to make glucose by gluconeogenesis, which is going to involve making glycerol, 2-phosphate, etc. And I also mentioned that this is a cycle, so we have to regenerate the ribose 1,5-bisphosphate, and that's the 3rd part of the cycle. The steps of this cycle are actually very similar to the non-oxidative phase of the pentose phosphate pathway. So I'll probably show that, but I'll just for comparison. It's essentially the same as this pathway with 2 additional steps that make the pathway reversible. So I think I'll stop here because I don't have time to do this today. And so I'll do that on Friday and maybe say a little bit more about this pathway. Are there any questions? Yes.
I'm sorry, what were you mentioning about stage 2 gluconeogenesis?
The gluconeogenesis is gluconeogenesis, so it's exactly the same. The only difference is that NADPH is used in reduction, but other than that, it's the same.